To locate a break in a buried cable, several methods can be employed, ranging from advanced tools to more basic techniques. Firstly, consider using a cable tracer, specifically a Time Domain Reflectometer, also known as a TDR. A TDR operates by sending a signal down the cable and measuring the time it takes for that signal to reflect back. Breaks or faults within the cable will cause a change in the reflection time, and this change can be used to pinpoint the location of the issue. While TDR are recognized as the most accurate method, it's important to note that they can be relatively expensive. Secondly, you can use a voltmeter in conjunction with a signal inducer, also known as a tone generator. To use this method, begin by connecting a voltmeter to the cable at the source. Next, use the signal inducer to send the signal down the length of the cable. As the signal travels, move the signal inducer along the path of the buried cable, all the while monitoring the voltmeter. The key to finding the break lies in observing the voltmeter reading. When the signal from the inducer reaches the point of the break, the voltage displayed on the voltmeter will drop significantly. This voltage drop indicates the approximate location of the fault. Thirdly, a similar method involves using a tone and probe. This approach shares similarities with the voltmeter and signal inducer method, but instead of a voltmeter, it uses a probe. The probe's purpose is to pick up the signal being transmitted by the inducer. As the signal travels along the cable and encounters a break, the probe will no longer detect the signal. This absence of signal detection helps you identify the location of the break in the cable. Fourthly, consider using a ground resistance meter. This method is based on the principle that breaks in aluminum cable often lead to a drop in ground resistance. To implement this, measure the ground resistance both at the source of the cable and at the destination, in this case, the barn. If there is a notable difference in the resistance measurements between these 2 points, it may be indicative of a break somewhere along the cable's length. Aside from these meter-based methods, there are also other suggestions to consider. Visual inspection can be helpful. Carefully examine the path of the buried cable for any visible signs of damage, breaks, or disturbances in the ground. Even though the cable is buried, sometimes external factors can cause noticeable changes on the surface. Another approach involves excavating sections of the cable. If the cable is not buried very deep, you could carefully excavate small sections along its length to visually inspect it for breaks. This can be a more labor-intensive method, but it allows for a direct assessment of the cable's condition. Furthermore, if the cable is part of a larger underground network, it's worth contacting the utility company. They may have existing records or specialized equipment that can assist in locating the break. In terms of affordable meters, there are a few options available. Klein Tools offers a cable tracer model C8600, which is typically priced around $150. Southwire also offers a signal inducer and amplified probe kit, generally available for approximately $50. For ground resistance measurements, the Extec EX510 ground resistance meter is an option with a price point of around $100. When working with electrical cables, remember to prioritize safety. Ensure that the power is disconnected before performing any tests or inspections. If you're not comfortable working with electricity, it's always best to consult a qualified electrician. The Time Domain Reflectometer, or TDR, is a sophisticated electronic instrument used to characterize and locate faults in metallic cables such as twisted pair coaxial cables and even power cables. It operates on the principle of sending an electrical signal, a pulse or a step, down the cable and then analyzing the reflections that return. The characteristics of these reflections provide detailed information about the cable's condition, including its length, impedance, and the presence and location of any defects or discontinuities. Here's a more in-depth look at how TDR works. Firstly, pulse generation. The TDR generates a short electrical pulse, typically with a fast rise time. The characteristics of this pulse, such as its amplitude and duration, are carefully controlled to optimize the measurement process. Secondly, signal propagation. This pulse is then launched into the cable under test. As the pulse travels along the cable, it encounters the characteristic impedance of the cable. In a perfectly uniform cable, the pulse would propagate without any reflections. Thirdly, reflection analysis, when the pulse encounters a change in impedance such as a short circuit, an open circuit, a crimp, a splice, or any other defect, a portion of the signal is reflected back towards the TDR. The TDR measures the amplitude, polarity, and arrival time of these reflections. Fourthly, distance calculation. The time it takes for the reflection to return is directly proportional to the distance to the impedance change. TDR uses the known propagation velocity of the signal in the cable to calculate the distance to the fault. The propagation velocity depends on the cable's dielectric properties and is usually specified by the cable manufacturer. Fifthly, impedance measurement. The amplitude and polarity of the reflection are related to the magnitude and type of impedance change. A short circuit will cause a large negative reflection, while an open circuit will cause a large positive reflection. The TDR can calculate the impedance at the point of reflection based on these measurements. Sixthly, display and interpretation. The TDR displays the reflection data as a function of time or distance on the screen. This display, called the TDR trace, shows the amplitude of the reflections on the vertical axis and the distance along the cable on the horizontal axis. Trained technicians can interpret the TDR trace to identify various types of faults and their locations. The TDR trace provides a visual representation of the cable's condition. A smooth flat trace indicates a uniform cable with no significant defects. Sharp peaks or dips in the trace indicate impedance changes, which can be caused by various types of faults. A large positive reflection indicates an open circuit, where the cable is broken or disconnected. A large negative reflection indicates a short circuit, where the cable conductors are connected unintentionally. Small reflections can indicate minor defects, such as crimps, bends, or poorly made splices. The distance to the fault is determined by measuring the time delay of the reflection and using the cable's propagation velocity. TDR come in various types, each designed for specific applications. Firstly, there are handheld TDR. These are compact, portable devices used for field testing and troubleshooting of cables. They are typically battery-powered and have a built-in display for viewing the TDR trace. Secondly, benchtop TDR. These are larger, more powerful instruments used in laboratories and manufacturing environments. They offer higher accuracy and more advanced features than handheld TDR. Thirdly, cable testers with TDR functionality. Many cable testers used for certifying and troubleshooting network cables include TDR functionality as one of their features. These testers can perform a variety of tests, including wire map, length, attenuation, and TDR measurements. TDR are used in a wide range of applications, including telecommunications, to locate faults in telephone and data cables, networking, to troubleshoot network cabling and ensure proper performance, aerospace, to test aircraft wiring harnesses and identify damaged or worn cables, power systems, to locate faults in underground power cables, cable manufacturing, to verify the quality and uniformity of manufactured cables, and construction, to inspect newly installed cabling systems. While TDR are powerful tools, they also have some limitations. The accuracy of the distance measurement depends on the accuracy of the cable's propagation velocity. The TDR may not be able to accurately locate faults in cables with complex structures or varying impedance. The interpretation of the TDR trace requires training and experience. Overall, the Time Domain Reflectometer is an essential tool for anyone working with metallic cables. It provides a non-destructive method for characterizing cables, locating faults, and ensuring proper performance. The voltmeter and signal inducer method relies on basic electrical principles to identify cable breaks. The equipment needed is relatively inexpensive and readily available, making it an accessible troubleshooting technique. Here's a detailed explanation of how this method works. Firstly, the equipment needed includes a voltmeter. This is a device used to measure the voltage between 2 points in a circuit. It should be capable of measuring alternating current, also known as AC voltages, in the range expected for the cable under test. A signal inducer, also known as a tone generator. This device generates an electrical signal, typically a tone, that can be injected into a cable. It consists of 2 parts, a transmitter that injects the signal and a receiver that detects the signal. Secondly, preparation is key. Begin by disconnecting the cable from the power source to ensure safety. Identify the two ends of the cable, the source, where the power is supplied, and the destination, where the power is intended to reach. Thirdly, connect the voltmeter. At the source end of the cable, connect the voltmeter between one of the conductors, either the hot or neutral wire, and ground. Note the initial voltage reading. This reading should correspond to the voltage supplied by the power source. If the voltmeter reads 0 volts, double-check the connections and ensure that the power source is active. Fourthly, inject the signal at the source end of the cable. Use the signal inducers transmitter to inject a signal into the conductor that is connected to the voltmeter. The signal inducer will generate a tone that travels along the cable. Fifthly, trace the cable at the destination end of the cable. Use the signal inducer's receiver to trace the cable's path. The receiver will pick up the tone generated by the transmitter. As you move the receiver along the cable, the tone will be audible as long as the cable is intact. Sixthly, locate the break. As you trace the cable, pay close attention to the voltmeter reading. When the signal inducer's receiver reaches the point where the cable is broken, the voltage reading on the voltmeter will drop significantly, potentially to 0 volts. This indicates that the break is located between the point where the voltage drops and the last point where the tone was audible. Seventhly, confirm the break. To confirm the location of the break, move the signal inducer's receiver back and forth around the point where the voltage dropped. The voltage reading on the voltmeter should change as you move the receiver across the break. This confirms that you have located the break. The voltage drop indicates that the electrical circuit is no longer complete. When the cable is intact, the voltage is present along the entire length of the cable. However, when the cable is broken, the voltage drops to 0 at the point of the break because the circuit is open. The signal inducer works by generating an electromagnetic field around the cable. The receiver detects this field and amplifies it, making the tone audible. When the cable is broken, the electromagnetic field is disrupted, causing the tone to disappear. This method is most effective when the cable is buried relatively shallow and the soil is not too conductive. In highly conductive soil, the signal from the signal inducer may be attenuated, making it difficult to trace the cable. It is important to use a voltmeter and signal inducer that are appropriate for the voltage and frequency of the cable under test. Always follow the manufacturer's instructions for the safe operation of these devices. The tone and probe method is a technique used to trace and identify wires or cables, typically in electrical or electronic systems. It involves injecting an audio frequency signal into the wire or cable and then using a probe to detect that signal along the wire's path. This method is particularly useful for identifying wires in bundles, tracing wires through walls or underground, and locating breaks or shorts in cables. The components of the tone and probe method include a tone generator, also known as a signal injector or wire tracer, which is a small electronic device that generates an audio frequency signal. This signal is typically in the range of 1 kHz to 3 kHz. The tone generator has two leads, one of which is connected to the wire to be traced, and the other is connected to a ground or reference point. A probe, also known as a tone probe or inductive amplifier, is a handheld device that detects the audio frequency signal injected by the tone generator. The probe has a tip that is placed near the wire or cable, and it amplifies the signal, making it audible through a speaker or headphones. To use the tone and probe method, firstly, prepare the wire or cable. Disconnect the wire or cable from any power source or active circuits to ensure safety. If the wire is part of a bundle, separate it from the other wires to avoid interference. Secondly, connect the tone generator. Connect one lead of the tone generator to the wire to be traced and the other lead to a ground or reference point. Make sure the connections are secure and that the tone generator is turned on. Thirdly, trace the wire with the probe. Turn on the probe and adjust the volume to a comfortable level. Hold the probe tip near the wire or cable and move it along the wire's path. The probe will emit an audible tone when it detects the signal injected by the tone generator. Fourthly, identify the wire. As you move the probe along the wire, listen for the loudest and clearest tone. This indicates that you have found the correct wire. If the tone is weak or intermittent, check the connections of the tone generator and make sure the probe is properly grounded. Fifthly, locate breaks or shorts. If the tone suddenly disappears or becomes very weak, it may indicate a break or short in the wire. To locate the break or short, move the probe back and forth along the wire until you find the point where the tone disappears. The tone and probe method works by using the principle of electromagnetic induction. The tone generator injects an audio frequency signal into the wire, which creates a small electromagnetic field around the wire. The probe detects this electromagnetic field and amplifies it, making the tone audible. The strength of the electromagnetic field depends on the current flowing through the wire. If the wire is broken or shorted, the current will be disrupted, and the electromagnetic field will be weakened, causing the tone to disappear. The tone and probe method is a versatile and reliable technique for tracing and identifying wires and cables. It is commonly used by electricians, technicians, and installers in a variety of applications, including electrical wiring, telecommunications, data networking, and automotive repair. When using the tone and probe method, it is important to follow some safety precautions. Always disconnect the wire or cable from any power source or active circuits before starting. Use a probe with insulated tips to avoid accidental contact with live wires. Be careful when working in confined spaces or near other electrical equipment. The ground resistance meter method is a technique used to assess the condition of grounding systems and to detect faults in electrical circuits. It involves measuring the resistance between a grounding electrode and the surrounding earth. This measurement provides valuable information about the effectiveness of the grounding system and can help identify potential safety hazards. The components of the ground resistance meter method include a ground resistance meter, which is a specialized instrument designed to measure the resistance of the earth. It typically consists of a current source, a voltage meter, and a display. Auxiliary electrodes, also known as test stakes, which are used to inject current into the earth and to measure the voltage drop caused by the current. These electrodes are typically made of metal and are driven into the ground at specific distances from the grounding electrode. Connecting wires, which are used to connect the ground resistance meter to the grounding electrode and the auxiliary electrodes. To use the ground resistance meter method, firstly, prepare the grounding electrode. Ensure that the grounding electrode is clean and free of corrosion. Disconnect the grounding electrode from any equipment or circuits to avoid interference. Secondly, position the auxiliary electrodes. Drive the auxiliary electrodes into the ground at specific distances from the grounding electrode. The distances between the electrodes should be determined based on the size and type of grounding system being tested. Thirdly, connect the ground resistance meter. Connect the ground resistance meter to the grounding electrode and the auxiliary electrodes using the connecting wires. Make sure the connections are secure and that the meter is properly grounded. Fourthly, measure the ground resistance. Turn on the ground resistance meter and take a reading. The meter will display the resistance between the grounding electrode and the surrounding earth. Fifthly, interpret the results. Compare the measured ground resistance value to the acceptable limits specified in the relevant standards and regulations. If the measured value is too high, it may indicate a fault in the grounding system or a problem with the earth conductivity. The ground resistance meter method works by injecting a known current into the earth through one of the auxiliary electrodes. This current flows through the earth and returns to the meter through the grounding electrode. The meter measures the voltage drop caused by the current and calculates the resistance using Ohm's law, which is voltage equals current times resistance. The resistance value is then displayed in the meter. The ground resistance meter method is a valuable tool for ensuring the safety and reliability of electrical systems. It is commonly used by electricians, engineers, and inspectors in a variety of applications, including power generation, distribution, industrial facilities, and telecommunications. When using the ground resistance meter method, it is important to follow some safety precautions. Always disconnect the grounding electrode from any equipment or circuits before starting. Use a meter with insulated probes and connecting wires to avoid accidental contact with live wires. Be careful when working in wet or damp conditions. It is important to note that ground resistance measurements can be affected by a number of factors, including soil type, moisture content, temperature, and the presence of underground utilities. Therefore, it is important to take these factors into account when interpreting the results. Visual inspection is a critical step in identifying potential issues with buried cables. It involves carefully examining the area above and around the cable's path for any signs of disturbance, damage, or other anomalies that could indicate a problem. While visual inspection cannot directly reveal the condition of the buried cable itself, it can provide valuable clues about potential problems that may warrant further investigation. Here are some key aspects to consider during a visual inspection. Look for signs of digging or excavation. Recent digging or excavation activity near the cable's path is a major red flag. It could indicate that the cable has been damaged by digging equipment. Pay close attention to areas where construction or landscaping work has been performed. Check for subsidence or ground movement. Subsidence, or sinking of the ground, can put stress on buried cables and lead to damage. Look for areas where the ground appears to be uneven or has settled. Similarly, ground movement, such as landslides or erosion, can also damage buried cables. Check for cracks or fissures in the soil. These could indicate that the ground is unstable and that the cable may be at risk. Look for signs of water damage. Water can corrode buried cables and cause them to fail. Check for areas where water is pooling or where the ground is excessively wet. Also, look for signs of erosion caused by water runoff. Check for vegetation stress. Changes in vegetation growth patterns can sometimes indicate problems with buried cables. For example, if the vegetation above the cable is wilting or dying, it could be a sign that the cable is leaking electricity or chemicals. Also, look for areas where the vegetation is unusually lush or green. This could indicate that the cable is providing an additional source of nutrients to the soil. Check for exposed cable or conduit. In some cases, buried cables may become exposed due to erosion or other factors. If you see any exposed cable or conduit, do not touch it. Contact a qualified electrician or utility worker to inspect the cable and make any necessary repairs. Check for markers or warning signs. Buried cables are often marked with signs or markers to indicate their location. Make sure that these markers are in place and that they are clearly visible. If any markers are missing or damaged, contact the utility company to have them replaced. Document any findings. It is important to document any findings from the visual inspection, including the location of any potential problems, the date and time of the inspection, and any photographs or videos taken. This information can be used to help diagnose the problem and to plan any necessary repairs. Excavating sections of buried cable is a method used to visually inspect the cable for damage or faults. It involves carefully digging up small sections of the cable to expose it for examination. This method is typically used when other non-destructive methods, such as cable tracing or ground resistance testing, have failed to locate the problem. Here are the steps involved in excavating sections of buried cable. Firstly, safety is paramount. Before beginning any excavation work, it is essential to ensure the safety of yourself and others. Call the local utility companies to locate any other buried utilities in the area. This will help you avoid damaging any other underground infrastructure. Wear appropriate personal protective equipment, including safety glasses, gloves, and sturdy footwear. Disconnect the power to the cable before starting any excavation work. Secondly, locate the cable. Use a cable locator or other means to determine the approximate location of the buried cable. This will help you avoid digging in the wrong place. Thirdly, carefully excavate. Use a shovel or other digging tool to carefully excavate the soil above the cable. Be careful not to damage the cable during excavation. Dig slowly and deliberately, and use hand tools when necessary to avoid damaging the cable. Fourthly, expose the cable. Once you have excavated enough soil to expose the cable, carefully clean the cable to remove any dirt or debris. This will make it easier to inspect the cable for damage. Fifthly, inspect the cable. Visually inspect the cable for any signs of damage such as cuts, cracks, or corrosion. Pay close attention to any areas where the cable may have been stressed or damaged. such as near joints or bends. Sixthly, document any findings. If you find any damage to the cable, document the location and extent of the damage. Take photographs or videos of the damage to help with repairs. Seventhly, backfill the excavation. Once you have completed the inspection, carefully backfill the excavation with soil. Compact the soil to prevent settling and to protect the cable. When excavating sections of buried cable, it is important to follow these precautions. Never dig blindly. Always use a cable locator or other means to determine the approximate location of the cable before digging. Dig carefully and deliberately. Avoid using heavy equipment that could damage the cable. Inspect the cable carefully. Look for any signs of damage, such as cuts, cracks, or corrosion. Document any findings. This will help with repairs and prevent future problems. Backfill the excavation properly. This will protect the cable and prevent settling. Contacting the utility company can be a crucial step in locating a break in a buried cable, especially if you suspect the cable is part of a larger underground network. Utility companies often have specialized equipment, detailed records, and expertise that can be invaluable in such situations. Here are several reasons why contacting the utility company is a good idea. They may have records of the cable's location. Utility companies typically maintain detailed maps and records of the underground infrastructure, including the location of buried cables. This information can help you pinpoint the cable's path and potentially identify the location of the break. They may have specialized equipment for locating faults. Utility companies often have specialized equipment, such as cable fault locators, that can precisely identify the location of breaks in underground cables. These devices use techniques like Time Domain Reflectometers, also known as TDR, or impedance testing to pinpoint the fault. They have trained personnel to assist. Utility companies have trained technicians and engineers who are experienced in working with underground cables. They can provide guidance on how to safely locate and repair the break. They can ensure the safety of the area. If the break in the cable is causing a safety hazard, such as a potential for electric shock or a fire, the utility company can take steps to mitigate the risk and protect the public. They can coordinate repairs. If the cable is part of the utility company's network, they will be responsible for coordinating the repairs. They can ensure that the repairs are done properly and that the cable is safely returned to service. Before contacting the utility company, gather as much information as possible about the cable, including its approximate location, its purpose, and any signs of damage or malfunction. Be prepared to answer questions from the utility company about the cable and the situation. When you contact the utility company, explain the situation clearly and concisely. Let them know that you suspect a break in a buried cable and that you need their assistance in locating and repairing it. Follow the utility company's instructions carefully. They may ask you to take certain precautions or to avoid certain activities. Cooperate with the utility company's personnel. They are there to help you resolve the problems safely and efficiently.